Welcome to our channel. Imagine looking up at the night sky and realizing that every star you see is not shining as it is right now, but as it was years, centuries, or even millions of years in the past. The universe doesn't show us the present. It shows us memories carried across unimaginable distances by a traveler that never slows down: light. In this video, we're going to uncover what a light year truly is and why it's so much more than a giant number. You'll learn how scientists first measured the speed of light, how we calculate distances between stars and galaxies, and why the sky above us is actually a vast cosmic time machine. We'll explore the history behind the light year, the tools astronomers use to chart the universe, and how this single concept changed our understanding of space forever. If you're ready to travel across time and distance without ever leaving Earth, make sure to like the video, subscribe to the channel, and let's begin. The idea of a light year has always felt like a quiet challenge to the human mind. It sits there in astronomy books and documentaries, sounding innocent and almost poetic. But the moment you try to picture it, something inside you hesitates. It's a distance so great that the normal tools we use to make sense of the world stop working. The meter on a map, the mile on a highway, the kilometer on a satellite image, all collapse under the weight of cosmic scale. A light year is a doorway into a level of distance that humans were never built to understand naturally. Yet we keep trying. And the more we try, the more we discover how small, fragile, and incredibly early we are in our understanding of the universe. Imagine the opening scene, a tiny dot in a vast darkness. That dot is Earth. The atmosphere glows faintly, almost embarrassed by how little it lights up compared to the surrounding space. Far beyond the Earth, sunlight fades into a thin whisper. Beyond the sun, the planets spin with quiet dedication. Beyond the planets, we enter a region where human imagination begins to stretch so far that it cracks a little. The distances between objects are no longer friendly. They no longer bend to our intuition. We step into scales that require new language, new measurements, and new ways of thinking. For thousands of years, humans had no idea how far the stars were. They looked fixed in the night sky, sprinkled like salt across a black table. People believed they were just past the clouds, or maybe on solid crystal spheres, or maybe lanterns carried by gods. Nobody worried about distance because nobody imagined that distance could be so immense. The mind stops where curiosity becomes uncomfortable. And for most of human history, thinking about star distances was uncomfortable. It felt like climbing a staircase that never ends. But curiosity refuses to stay quiet forever. It keeps pushing, tapping the shoulder of every generation, whispering questions that feel slightly dangerous. What are stars? How far are they? How long does their light travel before reaching us? These questions pulled scientists into a long and difficult journey, a journey that eventually produced one of the most powerful ideas in all of astronomy: the light year. To understand the light year, we have to understand why kilometers and miles become clumsy in space. Consider Earth. You can circle it in less than 45,000 kilometers. The Moon is only about 384,000 kilometers away. Mars is tens of millions. The Sun is 150 million. These numbers are already stretching our sense of distance, but they still fit inside the human brain with a little effort. But leave the solar system, and these numbers explode. The nearest star beyond the Sun is so far away that if we use kilometers, we would need more digits than most calculators could show without scientific notation. We don't easily imagine these numbers. They feel abstract, like financial figures from a distant government report that you know exist but cannot emotionally understand. This is why the light year became necessary. It compresses the unspeakable into something pronounceable. It ties distance to light, the fastest thing in the universe, something with a fixed and reliable speed. Light moves with a confidence that nothing else possesses. It travels 299,792 kilometers every second, without pause, without fatigue, without negotiation. If light had a personality, it would be the universe's most disciplined traveler. So now imagine that traveler moving through the void. 1 second, 2 seconds, 10 seconds. In each moment, it crosses distances our fastest spacecraft could never hope to match. Let it travel for a minute, and it has gone farther than any human-created object will go this century. Let it travel an hour, and it outruns our entire solar system. Let it travel a year, and it draws a line in space so long that human thought almost collapses trying to follow it. That line is a light year. Before this concept existed, astronomers struggled to explain faraway stars without drowning in numbers. They needed something that could express magnitude without overwhelming the human mind. But the light year didn't just appear suddenly. It grew out of centuries of scientific effort to understand something more fundamental: the speed of light. In ancient times, people argued about whether light had speed at all. Some believed light travelled instantly. Others suspected it moved, but simply too fast for human senses to detect. Galileo tried to measure it with lanterns on hills, which sounds brave but almost comically impossible, given how fast light actually moves. Still, he attempted it, and that attempt mattered. It was a small push toward a discovery that would rewrite physics. Then in the late 1600s, a Danish astronomer named Ole Rømer made a breakthrough using Jupiter's moon Io. He didn't need clocks or lasers or mountains. He just observed. He noticed that Io's eclipses didn't happen exactly when predicted. They were slightly delayed when Earth was moving farther from Jupiter and slightly early when Earth was moving closer. That delay was light's travel time. It was the universe quietly revealing a fundamental truth to someone patient enough to watch. From Rømer's work, the idea spread. Light has speed, real speed, measurable speed. Over the next 2 centuries, scientists refined this measurement again and again, using better instruments and stronger mathematics. Eventually, the speed of light became a constant of nature, a core piece of modern physics, and the anchor for Einstein's theory of relativity. Once the speed of light was known, the idea of travelling by that speed became intuitive. If light moves at a constant rate, we can treat its travel time as a ruler. 1 second equals this many kilometers, 1 minute equals more, 1 year equals a cosmic scale. When astronomers adopted the term light year, they weren't inventing something poetic. They were solving a practical problem. They needed a measurement that could handle the universe's arrogance, its refusal to be small, its refusal to be measured in the tiny units humans use to measure their daily lives. A light year offered that solution. It became a bridge between what we can see and what we can understand. The moment you hear the phrase, "the star is 4 light years away," your mind receives 2 messages at once. First, the star is unimaginably far. Second, the light you see left that star 4 years ago. Distance and time combine into one idea, one package, one elegant phrase. This is why the light year is more than a measurement. It's a story of how far light has travelled to reach you. It's a quiet reminder that everything you see in the night sky is not happening now. It has already happened. The universe is a memory, and every star is a time capsule. This idea invites you into a deeper way of looking at the night sky. When you gaze upward, you're not seeing the present. You're looking through layers of time. Some stars are a dozen years old in our eyes. Others are hundreds of years old. Galaxies are seen as they were millions of years ago. The oldest light we can detect comes from a time when the universe was only a newborn. Light years reveal a truth we rarely think about. We live inside a cosmic delay. Everything we know about the universe is delayed information carried to us by light, and this is only the beginning. Trying to understand distance in space is a bit like trying to hold water in your hands. No matter how tightly you cup your palms, most of it slips away. The human brain evolved to understand the distance from one village to another, the width of a river, the height of a tree, the span of a field. These are distances we can walk, climb, or measure with tools made from wood or rope. But the universe does not care about these limits. It stretches far beyond any landscape the human eye will ever see. When we attempt to describe it, with everyday units, we run into a wall made of sheer scale. That wall forces us to rethink how we talk about distance itself. Take the moon. It is only a short hop away in cosmic terms. Light takes a little more than 1 second to reach it. 1 second, that is less time than it takes to blink slowly. Yet that same blink cannot begin to contain the scale of a light year. If the moon is 1 second away at the speed of light, then the sun is 8 minutes away. The nearest star beyond the sun is more than 4 years away. The center of the Milky Way is more than 26,000 years away. And the nearest major galaxy is 2.5 million years away. These numbers don't sit comfortably in the mind. They aren't supposed to. They reveal a universe that is older, larger and stranger than anything humanity was originally prepared to understand. When astronomers first tried to measure star distances, they faced a nearly impossible challenge. The stars were too far away for direct measurement. A ruler couldn't reach them. A ship couldn't sail to them. Even a telescope couldn't simply zoom in and mark the distance. They needed a method that used the Earth's own motion. This method eventually became known as parallax. Imagine holding your thumb in front of your face and closing one eye, then the other. Your thumb shifts slightly against the background. That shift is parallax, and astronomers use Earth's orbit around the Sun to make a much larger version of that observation. By measuring how much a star appears to move when seen from different points in Earth's orbit, they can estimate its distance. But here is the twist: most stars appear so incredibly far that even this method struggles. The shift is so tiny that early astronomers could not even detect it. They looked through telescopes, hoping to see something move, but everything seemed firmly pinned to the sky, like jewels glued to a black curtain. It wasn't until the 1830s that Friedrich Bessel finally measured the parallax of a star. That moment changed history. For the first time, we had a real physical measurement of how far a star actually was. And the answer was shocking. Stars were not merely far, they were unimaginably, absurdly far. Distances so massive that nothing on Earth could compare to them. This discovery triggered a cascade of new thinking. If the stars were so distant, then their light must take years to reach us. If light takes years, then every star is a statement from the past. If every star is a message from a different time, the universe is not a single moment, but a layered archive of ancient events. This realization made the idea of the light year even more powerful. It became not just a unit of distance, but a unit of understanding. A unit that connects the physical universe with the history written in its light. Picture yourself standing under a clear night sky. You look up at a bright star. Maybe it is 10 light years away. That means the light, touching your eyes tonight, started traveling toward you when you were a child, or before you were born, or before your parents met. If the star is 100 light years away, the light left before your great-grandparents were born. If the star is thousands of light years away, the light began its journey before humans discovered farming or writing. The Milky Way becomes a museum of ancient light, each star a silent storyteller carrying memories across time. This is why the light year is such a compelling concept. It allows us to think about distance without drowning in meaningless numbers. 1 trillion kilometers means nothing to the average person. You hear the number, but your mind rejects it. A light year, on the other hand, feels like a unit with personality. It has character, it has weight, it has emotional resonance. It tells you not just how far something is, but how long its light has been traveling to reach you. When scientists describe the nearest star system, Alpha Centauri, as a little more than 4 light years away, it suddenly makes sense in a way that trillions of kilometers never could. 4 years. 4 years of light racing through space. 4 years of a cosmic messenger crossing the void at nearly 300,000 kilometers per second. Use kilometers and you get a number so huge it loses all meaning. Use light years, and the impossible becomes understandable. Even more fascinating is what happens when we scale up to larger structures. The Milky Way galaxy is about 100,000 light-years across. That means if a beam of light started at one edge and travelled straight across to the other, it would take 100,000 years to complete its journey. During those years, entire civilizations could rise and fall, continents could shift, ice ages could form and melt. Humanity itself could evolve in ways we cannot imagine. Light years turn the galaxy into a storybook of enormous chapters, each page separated by centuries. The idea stretches further. When scientists describe the distance to the Andromeda galaxy as 2.5 million light-years, they are saying something remarkable. The light we are seeing tonight from Andromeda began its journey long before the first humans walked on Earth. It left when our ancestors were still small, frightened creatures trying to survive among predators. Earth was a wild, ancient place, and yet that same light travels into your eyes now, telling you about a galaxy that existed in the deep past. This perspective is one of the most beautiful and unsettling parts of astronomy. The universe does not show us its present, it shows us its memories. And the farther away something is, the older the memory becomes. The light from the most distant galaxies took billions of years to reach us. When we look at them, we see the universe as it was when it was young, still forming stars, still shaping its structure. Light years, then, are not just distances, they are corridors through time. Thinking this way forces us to confront our own smallness, but it also offers comfort. The universe is vast, but it is also generous. It sends us light from every corner, carrying stories, clues, and evidence of how everything began. Without light years, we would not just misunderstand distance, we would misunderstand the universe itself. This is why the term has become so essential in science. It is not perfect for every measurement. Professionals often use parsecs for certain calculations, but the light year remains the most intuitive unit for describing the space between stars and galaxies to ordinary people. It is the bridge between the cosmic and the human, the infinite and the understandable. The more we explore this idea, the more we realize why measuring distance in space is not just a mathematical exercise, it is a philosophical one. Every light year reminds us that space is vast, time is ancient, and our place in the universe is tiny but meaningful. We are creatures who evolved on a small planet, but somehow we have developed the imagination to describe distances that stretch beyond our galaxy. The fact that we can even talk about light years is a victory of human curiosity. And this curiosity is what keeps pushing us deeper into the unknown. The story of how humans discovered the speed of light is one of the most fascinating chapters in the history of science. It didn't happen in a laboratory filled with lasers and mirrors, at least not at first. It began with simple observations, flawed experiments, brave guesses, and a stubborn desire to understand something almost invisible. Light had always been part of human life, but for thousands of years people never questioned how fast it traveled. It seemed instant. When you lit a torch, the darkness vanished immediately. When the sun rose, the world brightened without delay. The idea that light could have a measurable speed felt unnecessary, even strange. Ancient philosophers debated it, but none had evidence strong enough to settle the argument. Some believed light moved infinitely fast. Others believed it moved but too quickly to detect. No one imagined a universe where light not only had speed, but a speed so extreme that human senses could never perceive its motion. The real progress began when science stepped into the picture and curiosity transformed from speculation into measurement. Galileo attempted one of the earliest experiments in the 17th century. His method was simple, almost naive. He and an assistant each held a covered lantern and stood on two distant hills. Galileo uncovered his lantern. When his assistant saw the flash, he uncovered his own. Galileo tried to measure the delay between the two flashes, but of course, the method failed. The human reaction time is far slower than the speed of light. The delay Galileo measured came from human reflexes, not from the travel time of light. Still, this attempt mattered. It showed that someone had finally tried to measure the speed of something everyone thought was immeasurable. The true breakthrough came from a place nobody expected, Jupiter's moon Io. In 1626, a Danish astronomer named Ole Rømer noticed something strange. Io orbited Jupiter with a reliable rhythm, disappearing behind the planet at predictable intervals. But Rømer noticed that these intervals changed depending on where Earth was in its orbit. When Earth was moving away from Jupiter, Io's eclipses appeared delayed. When Earth was moving toward Jupiter, the eclipses happened earlier. Rømer realized that this difference was not caused by Io. It was caused by light itself taking longer to reach Earth, when the distance was greater. This was a revolutionary idea. Light had a finite speed, and the universe had quietly revealed it through the dance of a distant moon. Rømer's measurements were not perfect by modern standards, but they were extraordinary for his time. He showed that light took about 22 minutes to cross the diameter of Earth's orbit. Later, scientists refined the value again and again. Suddenly, the speed of light transformed from a philosophical question into a measurable reality. Once this door opened, others rushed through it. Scientists began using new technologies to refine the measurement. Mirrors, rotating wheels, and electric devices replaced lanterns and guesses. Each generation pushed the precision closer to the true value, until by the early 20th century, we reached the number we use today, about 1,792 kilometers every second. This number became more than a measurement. It became a cornerstone of modern physics. Einstein placed it at the center of his theory of relativity. It emerged as a cosmic speed limit, a value the universe respects with remarkable consistency. Nothing, not even imagination, can outrun light. And if nothing can outrun light, then light becomes the perfect messenger for measuring distances that nothing else can cross in a reasonable way. Once scientists understood the speed of light, the idea of a light year became inevitable. Imagine light as a tireless traveler gliding through the universe. It never slows, never loses its rhythm. Watch it move for 1 second. In that second, it covers nearly 300,000 kilometers. Watch it move for a minute, and it crosses a distance that would take spacecraft months to travel. Watch it move for an hour, and it moves beyond anything the human mind naturally imagines. Let it travel for a day, and it completes a journey that goes beyond the outer planets. Let it travel for a year, and you have a distance so large that words struggle, numbers stretch, and the human mind tries to turn away from the sheer magnitude. This is what makes the light year so powerful. It transforms the unimaginable into something nearly graspable. It attaches itself to time, something we understand easily, and uses that to explain distance, something we struggle with. The idea that light travels for 1 year feels like something the brain can almost visualize. It becomes a measurement rooted in motion, in time, in rhythm. The speed of light becomes a cosmic heartbeat, steady and unwavering. The invention of the light year was not an invention in the traditional sense. No one sat down and said, "Let's create a new unit." It emerged naturally from the understanding of light's speed and the need to describe the colossal spaces between stars. As telescopes improved and scientists measured more star distances, the numbers became impossible to communicate using kilometers or miles. The distances were too large for ordinary units. A new language was required, a language shaped by the universe itself. That language was the light year. Astronomers in the 19th century began using the term more frequently, and by the early 20th century, it became standard in communicating cosmic distances to the public. Professionals often prefer parsecs for technical work, but the light year remains the most intuitive unit for anyone trying to understand the universe beyond Earth's neighborhood. It has a poetic quality, a rhythm that sounds almost like a story. When someone says a star is 10 light years away, it creates a picture in the mind. It suggests time, distance, and motion all at once. It invites imagination. But this elegance hides complexity. The distance of 1 light year is about 9.46 trillion kilometers. This number is so large that the mind barely begins to process it. Yet the phrase 1 light year makes it feel manageable. This is the magic of the unit. It creates clarity while hiding the chaos of enormous numbers. Humanity needed this clarity in order to speak meaningfully about the universe. As the concept spread, people began to realize the deeper implication. Saying something is 10 light years away means we see it as it was 10 years ago. Saying something is millions of light years away means we see ancient light, older than human history. The light year became not just a ruler, but a time machine. It allowed us to look backward, across the ages, simply by looking up. This shift changed astronomy from a study of the present sky into a study of ancient cosmic events. Every telescope became a window into the past. This is why the speed of light and the light year are inseparable. One defines the other. One gives meaning to the other. Without the speed of light, the light year is just a phrase. Without the light year, the speed of light is just a number. Together, they create the foundation for everything we know about distance in the universe. When we say the universe is billions of light years across, we are using this single idea to measure creation itself. When we study galaxies at the edge of the observable universe, we rely on the steady pace of light to tell us how far back in time we are looking. The concept is so woven into astronomy that imagining modern science without it feels impossible. We often think we invented the idea of water measurement, but in truth the universe gave us one of its own. It gave us the speed of light. It gave us the consistency of that speed. And from that gift, we created a unit capable of holding the vastness of everything beyond our world. And so the journey continues, each light year stretching farther into the unknown, each beam of light carrying secrets from distant places, waiting for us to decode them. As astronomy advanced and our understanding of light became sharper, the idea of using it as a measuring tool began to feel not only logical, but necessary. The speed of light became more than a value written in a physics textbook. It became a bridge between human comprehension and cosmic reality. Once scientists realized that light moves at a fixed and unchanging rate through the vacuum of space, they gained something extraordinary, a natural ruler built into the universe itself. And this ruler did not depend on human invention. It did not rely on metal bars, wooden rods, or digitized counters. It was pure physics, unbending and universal. A ruler made of motion. This shift in thinking changed not only how we measure distance, but how we imagine the universe. Before the discovery of a reliable constant, units like miles or kilometers felt arbitrary in space. They were good for Earth, good for describing rivers and oceans, good for telling someone how far a city was. But they shrank in usefulness once the scale moved beyond our solar system. Science needed something that could stretch across the cosmos without breaking under the weight of huge numbers. The speed of light provided exactly that. It gave astronomers a way to talk about the universe using a cosmic language rather than a human one. Understanding why this works requires a small step into the nature of light itself. Light is an electromagnetic wave, and it behaves with extraordinary consistency. In a vacuum, it always moves at the same speed. It doesn't speed up or slow down. It doesn't care about the motion of the observer. It doesn't negotiate with anything. It simply travels at its cosmic pace, a pace so fast that ordinary life has no comparison. If a beam of light left your hand and circled the Earth, it would complete the journey more than 7 times in 1 second. Nothing else in the universe behaves like this. Light isn't just fast, it's a form of stability in a universe filled with chaos. This stability is what makes it a perfect measuring stick. If you know how fast something moves and you know how long it travels, you know how far it has gone. That simple relationship, speed multiplied by time, creates the foundation for the light year. Scientists realized that if light takes 8 minutes to reach Earth from the Sun, and if it takes more than 4 years to reach the nearest star, then measuring distance by the time light travels is far more intuitive than counting trillions of kilometers. The concept spread quickly. Astronomers found that they could describe vast distances without drowning in numbers too large to hold meaning. They began describing star distances as tens of light years, or hundreds of light years, or thousands. Suddenly, cosmic scale gained clarity. The numbers remained huge, but the idea felt approachable because time is something everyone understands. We live our lives through time. We feel it, measure it, remember it. Time is intimate, distance is not. By tying distance to time, the light year turned an impossible scale into something human beings could visualize, even if only faintly. But the beauty of the light year is not just mathematical, it's emotional. It holds a strange poetry. When you think of light traveling for a year, you imagine a beam drifting endlessly through darkness, moving with purpose and silent determination. It becomes almost alive, a traveler crossing the universe. It tells a story not just of where something is, but where it was. Every light year represents a span of time during which light has been on the journey to reach us. That adds depth to the night sky. It transforms every star into a historical record, not a present moment. This dual nature, distance and time, makes the light year unique. A kilometer is only a distance, a mile is only a distance. A light year is a distance and a delay, a measure and a message. When we say a star is 100 light years away, we mean we are seeing it as it was 100 years ago. If the star died 50 years ago, its death has not yet reached us. Its light is still traveling. We still see it shining. In this way, the universe becomes a place of illusions grounded in physics. Everything is real, but everything is late. This was one of the most profound realizations in scientific history. It changed how we see the universe. It revealed that the night sky is not a mirror of the present, but a mosaic of different eras. Some stars belong to our century. Some belong to ancient human civilizations. Some belong to a time before humans existed at all. And some, visible only through telescopes, belong to the early universe itself. A universe still forming stars, still assembling galaxies, still learning its own shape. All of this is communicated through the simple idea of a light year. As technology advanced, astronomers began to measure greater distances with even more precision. Telescopes grew bigger and more accurate. We learned to detect faint movements of stars, variations in brightness, color shifts caused by motion. Each tool expanded our reach. It was as if our cosmic ruler was stretching farther and farther across the universe. The further we measured, the more astonishing the numbers became. The Milky Way alone stretches about 100,000 light years from side to side. That means if light started at one edge and moved toward the other, it would take 100,000 years to complete the journey. That single fact is almost enough to silence anyone who hears it for the first time. It places humanity in a perspective that is humbling and deeply real. Even that distance, monumental as it is, pales in comparison to the separation between galaxies. The Andromeda Galaxy is 2.5 million light years away. Beyond that lies the Virgo cluster, tens of millions of light years distant. Beyond that, the supercluster structure stretches hundreds of millions of light years. And beyond that, the cosmic web extends billions of light years across. Every step into the universe multiplies scale in ways that make the imagination tremble. Yet through all of this, the light year remains a steady thread connecting our understanding. No matter how large the universe becomes, the light year remains clear. It keeps us grounded in a consistent measurement. something trustworthy in a place where nearly everything else is extreme. It turns bewildering distances into stories clearer than the numbers alone could ever express. Scientists today rely on the light year not because it is perfectly suited for all mathematical work. It isn't, but because it communicates. It translates the universe into terms that people can absorb. When astronomers share discoveries, they know that millions of kilometers will mean nothing to most listeners, but millions of light years will. The phrase has become embedded in our language, in our films, in our imagination. It belongs not only to science but to culture. In many ways, the light year is one of humanity's greatest conceptual tools. It takes something infinite and makes it understandable. It takes something cold and mathematical and makes it almost magical. It takes the unreachable and allows us to describe it with confidence. Now that this cosmic ruler exists, it shapes the way we explore the universe. It influences how we design telescopes, how we interpret data, how we search for planets, how we imagine life elsewhere. It reminds us that our place in the cosmos is small, but our ability to comprehend it is extraordinary. And with every new discovery, the light year continues its role, guiding us deeper into the unknown. The moment astronomers embraced the light year, a new chapter in the history of measurement began. For centuries, the world relied on units shaped by human life. The length of a foot, the stride of a pace, the stretch of an arm, the distance a horse could travel in a day. These units came from the human body or daily experience. They were born from the scale of life on Earth, but the universe does not operate on human scale. Its distances burst through those limits with casual ease, forcing astronomy to abandon earthbound measurement and adopt something that matched cosmic magnitude. This is why the light year is not just a unit. It is a breakthrough in thinking. But where did the idea itself first appear? Like many scientific concepts, the light year was not invented in a single moment. It emerged gradually as astronomers wrestled with the challenge of describing star-waste distances. After Olaruma proved that light had a measurable speed, and after scientists refined that speed again and again, a new possibility began to take shape. If light travels at a constant rate, then the time it takes to travel could become a measure of distance. This was a subtle idea at first, mentioned in discussions rather than declared outright. In the early 19th century, astronomers began using the phrase, "the distance light travels in a year," but it had not yet solidified into a formal unit. The phrase began spreading in scientific writings as telescopes became powerful enough to measure star distances using parallax. When Friedrich Bessel measured the distance to the star 61 Tygni in 1838, he described it in terms of astronomical units and kilometers, but the idea of relating it to light's travel time soon followed. Scientists realized that when you say a star is a certain number of light years away, you're giving a description that feels far more meaningful than a string of enormous numbers. It carried clarity, it carried charm, it carried the weight of cosmic time. By the late 19th century, the light year found its place in textbooks and astronomical literature. It wasn't immediately universal. Many professionals preferred the parsec for formal work because it fit neatly into parallax calculations. But the light year captured the public imagination in a way the parsec never could. It sounded natural. It sounded visual. You could picture a beam of light traveling for a year through space. That image made the unit instantly powerful. Once the term became widely used, it changed how people talked about the universe. Suddenly, statements like, "the nearest star is more than 4 light years away," had clarity. They revealed not just distance, but the time it takes for messages from the universe to reach us. This dual meaning made the light year one of the rare units that naturally explains itself. Understanding its calculation deepens the appreciation for it. A light year is the distance light travels in 1 year. To find that distance, astronomers multiply the speed of light by the number of seconds in a year. The speed of light in a vacuum is about 209,792 kilometers per second. Now imagine this speed repeating every second, like a heartbeat that never stops. Multiply it by 60 to get the distance traveled in 1 minute. Multiply again by 60 to find the distance in 1 hour. Multiply by 24 to find the distance in a day. Finally, multiply by 365 to find the distance light travels in an entire year. The result is a staggering number, about 9.46 trillion kilometers. A trillion is already beyond daily imagination, but trillions piled upon trillions form the landscape of the universe. When you say something is 1 light year away, you are describing a distance so immense it would take the fastest spacecraft ever built tens of thousands of years to reach. Yet because the unit is tied to time, the brain accepts it more easily than huge kilometer counts. The word year creates a familiarity. It feels closer to human experience, even while representing a scale far beyond it. This concept also carries a quiet revelation. If something is 100 light years away, then its light has been traveling for 100 years before touching your eyes. You are not seeing it as it is. You are seeing it as it was. That idea transforms astronomy. It means that telescopes are not simply watching distant objects. They are reading the past. They are time machines in the truest sense. Consider the history of the Andromeda galaxy. When you observe it, the light reaching you left that galaxy more than 2 million years ago. At that time, early human ancestors walked the Earth. The world was wild, cold, and unfamiliar, and yet the light from that distant galaxy traveled through the darkness for millions of years. Untouched, unbroken, carrying information across the cosmos. It finally arrives here, revealing a galaxy that no longer exists in the same state. The image is old, the light is ancient, the experience is profound. The light year helps us grasp this strange truth with elegance. It compresses ancient time into understandable language. It gives us a tool to translate cosmic history into human thought. Without it, the distances between stars and galaxies would feel incomprehensible. With it, the universe becomes at least partially readable. Another important part of the light year's usefulness comes from how it organizes the structure of the cosmos. For example, when we describe the Milky Way, saying it is roughly 100,000 light years across immediately creates a picture. It tells us how long light needs to travel from one side to the other. It lets us imagine the galaxy as a vast disk of stars, glowing dust and swirling arms, a structure so large it feels more like an entire universe than a single galaxy. The same applies to clusters of galaxies. When scientists say the Virgo cluster is tens of millions of light years away, the mind understands it as distance and as time. It becomes clear that galaxies move, evolve, and collide over time spans far longer than human history. The light year makes these concepts approachable. It also helps clarify something essential about the observable universe. The farthest galaxies we can see are billions of light years away. Their light began its journey when the universe was young, dense and glowing with early heat. Every beam of light stretching across billions of years is a fragile messenger from an ancient epoch. Without the concept of the light year, explaining this journey would be nearly impossible. This unit also guides how we explore deeper space. When scientists design telescopes, plan surveys, or study star formation, they think in light years. The distances between objects determine how much power a telescope needs, what wavelengths of light it must capture, and how long it must observe. Light years influence not only what we see, but what our instruments must be capable of seeing. Even our search for exoplanets is shaped by this idea. When astronomers find a world orbiting a distant star, they describe it in light years. This immediately tells us how old the information is and how difficult it would be for a spacecraft to reach it. The light year reminds us that even the closest, potentially habitable planets are far beyond current human reach. It brings humility and wonder together. In the end, the light year is more than a unit of measurement. It is part of the language of modern astronomy, a tool that expresses both magnitude and meaning. It reflects a simple truth: the universe is enormous, and we are learning how to describe it one unit at a time. The creation and adoption of the light year show how humanity adapts its thinking to match the enormity of the cosmos. It is a symbol of our determination to understand a universe that continually challenges our imagination. And so we continue measuring, imagining and learning, guided by a unit born from the steady, unchanging speed of light. It is one thing to hear that a light year is the distance light travels in a year. It is another thing entirely to sit with that idea and try to feel the magnitude hidden inside it. The calculation is simple on paper, but overwhelming in reality. To understand what a light year truly represents, imagine following a single beam of light from the moment it leaves its source. Imagine its journey not as a number, but as an experience. Begin with 1 second. Light moves almost 300,000 kilometers in that brief moment. If you could somehow keep up with it, even for that single second, you would outrun every rocket, every spacecraft, every machine humanity has ever built. You would leave Earth behind, not gradually, but instantly. In that 1 second, you would circle the planet more than 7 times. This is the scale of light's motion. Even a single second feels unbelievable. Now stretch that second into a minute. 60 seconds of relentless movement. During that time, light crosses a distance so immense that even the orbit of the moon starts to feel small. The human mind begins to lose its grip on the visualization. We can imagine a car driving for a minute, a plane flying for a minute, but nothing we have ever experienced travels like light. It breaks intuition. It pushes against the limits of imagination. Let the beam continue for an hour. At this point, it has crossed a distance far beyond the boundaries of the outer planets. An hour of light's journey covers more ground than our fastest spacecraft could travel in decades. A single hour of light contains more distance than the history of human exploration combined. Let it travel for a day, 24 hours of uninterrupted motion. Now we arrive at a distance so massive that the mind simply yields. A day of light's travel moves far beyond the sun's reach and into the emptiness of interstellar space, and yet even this enormous stretch of distance is tiny compared to what light covers in a full year. When you multiply the speed of light by the number of seconds, in 1 year, you arrive at a number so vast it almost defies expression. About 9.46 trillion kilometers. That is 1 light year, a distance so immense that if you turned it into a road and drove along it at highway speed, you would need millions of years to finish the trip. If you flew at the speed of a commercial jet, the journey would last longer than the existence of the human species. Even the fastest spacecraft humanity has ever launched would require tens of thousands of years to reach a point just 1 light year away. This is why the light year is such an elegant and necessary unit. It transforms an impossible scale into something meaningful by tying it to time. Time is familiar. We live our entire lives inside it. We count it, plan it, feel it. When distance becomes too large for ordinary numbers, tethering it to a year gives the mind a handle to hold on to. But the light year is more than a convenient simplification. It reveals deep truths about the nature of the universe. Every light year represents a slice of time during which light has traveled freely through space, untouched, unbroken. This means that when we measure distance in light years, we are also measuring age. The farther away something is, the older the light we receive. This connection between distance and time is unlike anything else in science. Think of a star that is 50 light years away. When you look at it tonight, you are seeing it as it appeared 50 years ago. The star might have changed since then, grown hotter, dimmer, or even exploded, but its changes have not reached us yet. They are still traveling through space. We live inside this delay. Everything we see in the night sky belongs to a different moment in cosmic history. This effect becomes even more striking when we observe galaxies. The Andromeda Galaxy is about 2.5 million light-years away. The light that touches your eyes tonight set out long before humans learned to use tools or make fire. The world was wild, filled with early ancestors who had no idea that distant galaxies even existed. Yet the light they never saw continues its journey, finally reaching us in the present. Push the scale further. Some galaxies are hundreds of millions of light-years away. Some are billions of light-years away. When we observe these galaxies, we are witnessing the universe as it was before Earth even formed, before the oceans appeared, before life began, before the solar system existed at all. We are looking into epochs so ancient that human language barely has words for them. And yet, thanks to the light year, these vast distances become understandable. They become part of a story our minds can follow. The universe is not showing us its present, it is showing us its memories. The farther we look, the older the memories become. This is why astronomers often describe telescopes as time machines. A telescope does not change time, but it reveals time. It allows us to collect light that has been traveling for millions or billions of years. Without the concept of the light year, this experience would be impossible to explain. The light year is the key that unlocks the idea that looking deeper into space is the same as looking deeper into the past. The calculation of a light year also highlights something profound about the scale of the cosmos. If it takes light, nature's fastest messenger, a full year to cross a certain distance, then that distance must be unimaginably vast. When astronomers say the Milky Way is 100,000 light-years across, they're saying light needs 100,000 years to travel from one side to the other. 100,000 years ago, humans were still learning how to survive in harsh environments. Civilization did not exist. Writing did not exist. Cities did not exist. Yet a beam of light beginning its journey back then would only now reach the opposite side of our galaxy. This comparison helps ground the enormity of cosmic distances. It places human history beside cosmic history and reveals the scale difference between them. Human time becomes a thin layer on top of an ancient, sprawling universe. Consider how far humanity has traveled physically compared to the scale of a single light year. The farthest any human being has traveled is the Moon, which is about 1 light second away at the speed of light. Our spacecraft have reached the outer regions of the solar system, but they move so slowly compared to light that even a single light day lies far beyond our reach. Light days, light months, light years, each represents a magnitude of distance that spacecraft cannot currently approach. The light year defines the gap between human capability and cosmic immensity. It sets a boundary for imagination and ambition. It shows us how far we have come and how far we still have to go. Yet, despite this vastness, the light year also creates a sense of connection. It reminds us that the universe, no matter how large, communicates with us constantly through light. Every star we see is reaching out across light years, sending signals in the only language the universe uses, light itself. We receive these signals and decode them, learning about temperature, age, composition, and motion. Light crosses the unimaginable and brings us knowledge. The calculation of a light year reveals a universe that is immense but not unreachable in understanding. We may never travel a light year physically, but we can measure it, describe it, imagine it, and explore it through the light that reaches us. A single beam of light, moving steadily for 1 year, becomes a symbol of the universe's vastness and its clarity. It becomes a reminder that even in the enormity of space, there is order, there is structure, there is meaning. The light year is the bridge between human thought and cosmic distance, a unit that transforms bewildering emptiness into something we can study, admire, and try to understand. The more scientists worked with the concept of the light year, the more they realized why ordinary units could never survive the demands of astronomy. Miles, kilometers, and even astronomical units collapse under the pressure of the cosmic scale. They become clumsy, unwieldy, and almost comical when applied to interstellar distances. Imagine writing the distance to the nearest star as more than 40 trillion kilometers. The number becomes a wall of digits, intimidating and almost meaningless. It does not help you understand anything. It only reminds you how tiny human scales are compared to the universe. The light year solved this problem by compressing vast distances into manageable expressions. Instead of counting trillions of kilometers, astronomers could say a star was 4 light years away. Instead of describing the width of the Milky Way as a number with 14 zeros, they could say 100,000 light years. The difference in clarity is enormous. One sounds like a number, the other sounds like a story. Human language shapes human understanding. If you cannot describe something clearly, it becomes difficult to imagine. Before the light year, the cosmos felt like a bottomless abyss, filled with numbers too large to articulate. After the light year, the universe began to organize itself into a landscape we could describe, divide, compare, and explore with words that carried meaning rather than confusion. There is also something inherently elegant about using time as a measurement of distance. Time feels natural. Every person understands a year. We feel its rhythm. We live inside it. We recognize its passing. We count birthdays, anniversaries, seasons, and cycles. Time is intimate in a way distance is not. When you say light travels for 1 year, the mind immediately forms an instinctive sense of duration. Distance becomes easier to grasp when tied to something familiar. This elegance becomes even more valuable when working with incredibly large scales. Imagine 2 galaxies separated by 200 million light years. The number becomes more digestible because it conveys not just space but age. It tells us that the light traveling between them takes 200 million years to cross that gulf. When we observe either galaxy, we see it as it was long ago. In this way, the light year turns cosmic geography into cosmic history. Another reason astronomers prefer light years is practicality. Space is not arranged neatly. The gaps between planets, stars, and galaxies vary enormously. The distance from Earth to the Moon is tiny compared to the distance between stars, but huge compared to the height of mountains. Trying to describe all these distances with a single unit, like kilometers, creates confusion. The values change by orders of magnitude so dramatically that they lose relevance. Light years simplify the higher end of this scale. They give astronomers a consistent way to communicate distances beyond the solar system without drowning in gigantic numbers. This shift has shaped not only how professionals speak, but how the public imagines the cosmos. When documentaries describe a star as 10 light years away, that simple phrase transports viewers into the structure of the universe. They understand they are dealing with something far bigger than anything on Earth. Yet they do not feel overwhelmed by numbers. Instead, they feel invited into the scale rather than excluded by it. There is a deeper psychological reason for this as well. Humans naturally think in narratives. Our minds grasp stories more easily than raw data. The light year transforms distance into narrative. It turns measurement into motion. It implies a journey, a year-long journey of a beam of light racing through darkness. When you say 30 light years, you're not just stating a distance. You're describing a voyage that lasts 30 years at the universe's highest speed. That storytelling quality is what makes the light year resonate in popular imagination. Scientific clarity and emotional resonance combined make the light year one of the most powerful conceptual tools in astronomy. But this raises an important question. Why don't scientists use kilometers anyway, since they are the official SI unit? The answer lies in usability. When distances reach beyond the solar system, kilometer values become astronomically large, requiring scientific notation for almost every measurement. Scientific notation is extremely useful for equations, but in spoken communication, writing, or teaching, it becomes unwieldy. Telling someone the Andromeda Galaxy is 2.365 x 1022 meters away does not help them understand anything. Telling them it is 2.5 million light years away does. Even within the scientific community, the light year plays a crucial communicative role. Researchers may calculate using parsecs or other units, but when they present their findings to broader audiences, including experts from other fields, they often convert distances into light years for clarity. A biologist or geologist may not be fluent in parsecs, but everyone intuitively understands the idea of light traveling for a year. The light year also has another advantage. It sets a natural boundary between the solar system and the stars. Almost everything within the solar system lies within a few light hours or light days. Anything in the interstellar neighborhood lies beyond 1 light year. The moment something crosses the threshold of a light year, you know instantly that it belongs to a different scale of existence. It's no longer part of the solar system's architecture. It belongs to the galactic landscape. The psychological power of this boundary cannot be overstated. It divides our immediate cosmic home from the larger universe with a clean conceptual line. It's similar to the way people divide countries by continents or land by oceans. The light year creates a natural category in the mind. Another reason astronomers prefer light years is that the universe is constantly expanding. As galaxies drift apart due to cosmic expansion, the distances between them become more dynamic and more difficult to express using ordinary units. Light years offer a stable way to discuss distances in terms of observed light rather than actual moving boundaries. While expansion affects the true distance between galaxies, the light year tells us how long their light has been traveling. This method bypasses the complication of shifting cosmic geometry and focuses on something measurable and constant. This also matters when communicating astronomical discoveries. When scientists observe a galaxy whose light has traveled 12 billion years to reach us, they are not simply describing a location, they are describing an era, a chapter from early cosmic history, a time when galaxies were still forming their first generations of stars. Without light years, the ancientness of this light would be difficult to express. The light year also clarifies something fundamental about space travel. When we try to imagine interstellar journeys, kilometers offer no useful perspective. But when we say a star is 4 light years away, a new understanding forms. Even if humanity builds spacecraft that travel a significant fraction of the speed of light, the journey would still take years, decades, or centuries. Light years highlight the challenge and scale of interstellar exploration without needing complicated mathematical explanation. And this leads to a humbling truth. For all our technological progress, we live in a universe where even our fastest machines are painfully slow compared to light. A spacecraft traveling at tens of thousands of kilometers per hour seems impressive on Earth, but compared to the scale of a light year, it barely moves. The light year reminds us of the enormous gap between human capability and cosmic distances. Yet paradoxically, this same unit gives us hope. Because the universe communicates with us through light, we do not need to physically travel these distances to study them. Light does the traveling for us. The cosmos sends us information across thousands or millions of light years. Our telescopes simply catch it. This makes astronomy one of the few sciences where we can study things unimaginably far away without ever leaving our planet. The light year becomes a symbol of this connection. It represents both separation and communication. It marks the gulf between stars, but also the bridge made by light itself. It shows the limits of our reach, but also the power of our curiosity. In the end, the light year is not just a tool for scientists. It is a way for humanity to speak about the universe with confidence and clarity. It allows us to describe vast distances without fear, to explore ancient light without confusion, and to imagine the cosmos not as an impossible void, but as a landscape we can slowly map, understand, and appreciate. The deeper you explore the idea of the light year, the more you realize it carries a quiet mystery that sits at the heart of astronomy. It is not just a measure of distance, it is also a measure of time. This connection between space and time is not something humans were prepared to understand easily. We live in a world where distance and time feel separate. You walk a certain number of kilometers. You wait a certain number of minutes. Nothing in everyday life suggests that distance and time should merge into a single idea. Yet in the universe, they do. The light year forces us to accept that when you look across space, you're also looking across time. To understand this more deeply, imagine a dark, clear night. You step outside, look up, and see a sky filled with stars. Some are faint, some are brilliant, some form familiar shapes and constellations you may have known since childhood. But none of these stars are as they appear today. Not one. Every star you see belongs to a different moment in the past, depending on how far away it is. The night sky is not a photograph. It is a time mosaic, a layered story scattered across space. Take a star 10 light years away. The light entering your eyes tonight left that star 10 years ago. It traveled through cold, silent space during those 10 years, untouched, unchanged, carrying the last image of the star's surface from a decade earlier. If something dramatic happened to that star, if it flared, dimmed, or exploded, it has not yet reached you. You are still seeing the star's older face, a version frozen in time until new light arrives. Now consider a star 100 light years away. The light you see tonight began its journey a century ago. It began traveling before many people alive today were born. It left the star before airplanes crossed the sky, before radios hummed, before the world changed through wars, inventions, and discoveries. The light is older than modern history. It has been drifting across the universe for 100 years, and yet it still reaches you with perfect precision. Push the distance even farther. Move to the heart of the Milky Way, where stars are thick and dust clouds swirl like cosmic rivers. The center of our galaxy is about 26,000 light years away. The light from that region began traveling when humanity was still in the earliest stages of forming civilizations. The world was filled with ancient empires, stone tools and small communities learning to shape their future. 26,000 years of history passed on Earth. Agriculture, writing, cities, kingdoms, philosophies, religions, wars, migrations. And only now does that ancient light reach our telescopes. This is what the light year reveals. The universe does not show us the present. It shows us the past. And the deeper we look, the older the past becomes. This becomes even more astonishing when we move beyond our galaxy. Consider the Andromeda Galaxy, the nearest large galaxy to the Milky Way. It is about 2.5 million light years away. That means the light reaching you tonight left Andromeda when early humans were just beginning to walk the Earth. Our ancestors at that time were primitive beings, discovering fire, gathering food, and learning how to survive in a harsh world. Meanwhile, the light from Andromeda began its immense journey, crossing intergalactic space, untouched by anything, until it finally met your eyes or the lens of a telescope. That is the power of a light year. It transforms simple observation into a journey backward through time. The farther astronomers look, the earlier the universe becomes. They begin to see galaxies forming their first stars, clouds of gas collapsing under gravity, and chaotic structures shaped by forces still settling into order. When telescopes like Hubble or the James Webb Space Telescope observe galaxies billions of light years away, they are not seeing old galaxies, they are seeing young galaxies. Galaxies as they were shortly after the universe began. This strange connection between distance and time exists because light takes time to travel. Nothing moves faster than light, so nothing can deliver information faster. When we observe the universe, we are always looking at the speed limit of reality. Time and distance flow together. That is why astronomers often say, the farther you look into the universe, the farther back in time you see. Even the most distant light we know of, the cosmic microwave background, carries this idea to its maximum. This faint radiation is about 13.8 billion light-years old. When scientists detect it, they are observing the universe as it was shortly after the Big Bang, a universe still glowing with leftover heat from its birth. It is a snapshot from an era billions of years before galaxies formed. Without the concept of light years, this phenomenon would be incomprehensible. This link between light and time also reshapes how we interpret cosmic events. A supernova exploding 50,000 light-years away might light up a region of the galaxy with unimaginable brightness. But humanity will not see that explosion until 50,000 years after it happens. No telescope, no instrument, no spacecraft can detect it earlier. The information is locked inside the speed of light. If a star went supernova right now, somewhere in the Milky Way, and that star was 30,000 light-years away, the explosion already happened 30,000 years ago, but we have not seen it yet. The light is still on its way, crossing the void, carrying the message of that ancient event toward our future. In this sense, the future of astronomy is already written in the sky. It just has not arrived yet. This concept also gives cosmic structures an emotional weight. When we study stars that are dying or forming planets, we are not witnessing their current conditions, we are studying their old lives. Their past becomes our present observation. This creates a strange, beautiful connection between every point in the universe. Everything we see is a message from a different era, a reminder that time stretches in many directions depending on where we look. The light year is what lets us unify this cosmic relationship into a simple understanding. It transforms distance into something with depth. It allows us to grasp the enormous scale of space without drowning in numbers. It allows astronomers to decode the universe like a historian studying ancient documents, except the documents are beams of light traveling across unfathomable distances. This merging of time and distance also shapes the goals of astronomy. When scientists design telescopes, they think in light years. They calculate how faint and how ancient the light will be. They decide whether a telescope must be able to see something 100 million light-years away or 10 billion light-years away. Their instruments must catch fragile photons that have traveled across cosmic eras. Without the light year, predicting what telescopes can see would be nearly impossible. Even in science fiction, the idea of the light year dominates storytelling. When writers talk about distant planets, star colonies, or galactic wars, they often describe distances using light years because it instantly conveys scale. It tells the audience that the story takes place far beyond familiar worlds, in regions of space so distant that time itself becomes a character. But in the real universe, the light year does something even more astonishing. It shows us that we exist in a universe filled with ancient light, constantly streaming toward us from every direction. We are surrounded by messages that began long before our world existed. Everything we know about the cosmos, its age, shape, birth, evolution, comes from light that traveled across light years to reach us. This revelation is humbling. It tells us that the universe is not just big, it is old in ways that stretch the imagination, and yet, despite its age and immensity, it speaks to us through light. It allows us to witness its earliest moments simply by developing the tools to catch its oldest photons. This is the gift of the light year. It transforms cosmic silence into information. It transforms immeasurable distances into understandable time. It transforms the night sky into a living history of the universe. When astronomers look inside the Milky Way, the light year becomes more than a measurement. It becomes a map. It forms the backbone of how we understand our home galaxy. Its structure, its neighborhoods, its clusters, and the enormous gulf separating one region from another. The Milky Way is not a small friendly island of stars. It is a sprawling spiral system with billions of suns, countless planets, swirling arms of gas and dust, and a dark center holding everything in its gravitational grip. To truly appreciate its scale, you must see it in light years, not kilometers or miles. Only light years can express the enormous distances that define our galactic landscape. Start with our tiny corner of the galaxy. The Sun sits inside a minor spiral feature known as the Orion Arm, a thin branch tucked between two major galactic arms. We live in a calm neighborhood, far from the violent center and far from the outer fringes. The nearest star system beyond the Sun is Alpha Centauri, a little more than 4 light years away. This is the closest any other star gets to us. 4 years of light's travel may sound manageable when spoken aloud, but in reality, it is an extraordinary separation. If our Sun shrank to the size of a coin, Alpha Centauri would be another coin sitting hundreds of kilometers away. That is how empty space truly is. The stars seem close in the night sky only because the sky flattens their distance. The light year reveals the truth. The universe is mostly emptiness. Travel outward from our solar system using the scale of light years, and the structure of the Milky Way begins to emerge. Stars are not evenly spaced. Some regions are dense, filled with clusters where young stars are forming in great numbers. Other regions are sparse, with vast pockets of darkness where only dust clouds drift. The distances between neighboring stars average a few light years, but the sizes of these neighborhoods span hundreds or thousands of light years. The galaxy's major structures are measured in tens of thousands of light years. Only the light year can describe these regions without being swallowed by kilometers too huge to read. The thickness of the Milky Way's disk is itself remarkable. The thin disk where most stars reside is about 1,000 light years thick. That sounds like a clear number until you try to imagine it. 1,000 years of light travel, straight up from the galactic plane to reach empty space. If light began at the top edge of the disk when ancient civilizations first formed on Earth, it would only now be reaching the bottom edge of the disk today. Light years turn this abstraction into a sense of vast vertical structure. But the width is even more overwhelming. The Milky Way is roughly 100,000 light years across. That means if a beam of light started at one end and moved straight across to the other, it would take 100,000 years to complete the journey. In that time, humanity would evolve, languages would rise and fall, continents might shift, and ecosystems would change entirely. This is the size of the galaxy we call home, a disk so vast that light itself needs 100 millennia to cross it. Inside this immense structure are regions of intense activity. Some star-forming clouds, like the Orion Nebula, lie a little over 1,000 light years away. These regions glow brightly in telescopes, filled with newborn stars still wrapped in wisps of gas. The light reaching us from these regions carries stories of cosmic youth, light that began traveling around the time great civilizations of the past were just beginning to appear. Other places hold older stars, ancient clusters that formed billions of years ago. Many of these globular clusters orbit the outer halo of the Milky Way, at distances ranging from tens of thousands to more than 100,000 light years. The light from these clusters is ancient. When those photons began traveling toward Earth, our planet itself was a young, molten world with no oceans, no life, no continents as we know them today. Light years allow us to place such deep history into perspective, but even more astonishing is how the light year helps reveal our location in this vast cosmic structure. The Sun orbits the center of the Milky Way once every 230 million years. That journey takes us through regions separated by thousands of light years. Light from the galactic center takes 26,000 years to reach us, which means we are observing the center as it was before recorded human history began. The giant black hole at the heart of our galaxy, Sagittarius A, sends out radiation and energy that we detect only after it has travelled for tens of thousands of years. Every observation of the centre is a delayed message from a time when mammoths walked the Earth. As telescopes grew more powerful, astronomers began using light years to map spiral arms and trace the flow of stars across the galaxy. They discovered giant molecular clouds, hundreds of light years long. They found supernova remnants, where explosions sent shockwaves racing across space. They located vast, empty bubbles carved by ancient stellar winds. These structures make sense only when measured in light years. They vanish into chaos if described using kilometers. Consider the Carina Nebula, a colossal, star-forming region more than 8,000 light-years away. Its scale is staggering. Great pillars of gas stretching dozens of light-years high, pockets within which massive stars explode in brilliant supernovas. Cavities cleared by winds travelling at extreme speeds. When you hear that these structures span tens of light-years, you immediately understand you're dealing with features that would take tens of years for light, and therefore thousands of years for any spacecraft to cross. Move deeper into the galaxy, and you encounter regions with even more staggering scales. The galactic bulge, the dense central region, holds billions of stars packed into a structure, thousands of light-years thick. Light from those stars takes tens of thousands of years to arrive. Imagine receiving a message today from a civilization that may have vanished before humans learned how to plant seeds. That is the scale of the center. The galaxy's outer halo is even more mysterious. Here, globular clusters filled with ancient stars orbit silently, like lanterns floating on the edge of the galaxy's gravitational field. Some lie more than 100,000 light-years away from the center. They are relics from the early universe, fossils suspended in space. The light from them is incredibly old, older than human civilization, older than Earth's familiar landscapes, older than nearly everything we know. The light year gives us a language to describe their remoteness and their age. When astronomers chart the motion of stars, they use light years to measure how far stars drift over time. In human lifetimes, stars seem fixed, but over tens of thousands of years, they move across space, shifting positions as they orbit the galactic center. Their movement becomes visible only over spans measured in light years. The galaxy is alive, dynamic, ever-changing, but on timescales too large for human senses. The light year exposes this hidden motion, revealing that the night sky is not static at all, but constantly evolving. This measurement also helps identify the Milky Way's neighbours. The Large and Small Magellanic Clouds, two irregular dwarf galaxies, lie about 160,000 and 200,000 light-years away. These numbers tell us two things at once. First, that these galaxies are extremely close compared to most others. Second, that their light still takes hundreds of thousands of years to reach us. These dwarf galaxies may someday merge with the Milky Way, but that event lies billions of years in the future. The light year anchors this distant future in understandable terms. Inside the Milky Way, the light year becomes the essential unit for describing everything, from the distance to star clusters, to the size of nebulae, to the width of spiral arms, to the separation between major structures. Without it, the galaxy would be nothing more than a blur of impossible numbers. With it, the Milky Way becomes navigable in the imagination, a place with size, shape, and story. And through all of this, the light year continues to remind us of a simple truth. Even within our own galaxy, we see only the past. Every star, nebula, and cluster shows us a moment frozen in time. The Milky Way is not the galaxy of today. It is the galaxy of thousands of years ago. We live inside a cosmic time delay, surrounded by ghosts of past events, revealed to us through the slow but steady travel of ancient light. As we move beyond the boundaries of the Milky Way, the light year transforms again. Inside our galaxy, it helps us understand star clusters, spiral arms, and the geometry of our home system. But outside the Milky Way, the light year becomes something even more profound. It becomes the only language capable of describing the enormous structures that fill the universe. Galaxies, galaxy clusters, superclusters, and vast cosmic filaments stretch across distances so immense that even the light year begins to strain under their scale. And yet, without it, these structures would be impossible to comprehend. Start with Andromeda, our closest galactic neighbour. It lies about 2.5 million light-years away. This alone feels like a staggering distance, but in the cosmic landscape, it is practically next door. The light reaching us from Andromeda tonight left that galaxy long before humans learned how to make tools or control fire. It left before rivers carved their familiar channels, and before mountains eroded into the shapes we see today. 2.5 million years of darkness, motion, and silence passed before the light touched Earth. The light year captures this ancientness effortlessly. It allows us to feel the age of that message in a way that numbers alone never could. But Andromeda is only the first step. Surrounding the Milky Way is a group of smaller galaxies collectively known as the Local Group. It contains more than 50 galaxies spread across a region about 10 million light-years wide. Within this structure, galaxies drift, orbit, and occasionally collide over spans of time too long for human history to witness. These distances cannot be captured with kilometers. They defy everyday intuition. The light year is the only unit that turns this region into something we can understand. Move further outward, and the scale explodes again. Beyond the Local Group lies the Virgo cluster, a massive concentration of galaxies about 50 million light-years away. This cluster contains thousands of galaxies bound together by gravity. The light from these galaxies began traveling when dinosaurs still dominated Earth. The age of that light stretches beyond imagination, yet the light year brings that ancientness into a single phrase. The Virgo cluster is 50 million light-years away. The moment you hear the number, you understand both the distance and the time delay. This is where the light year begins to reveal something extraordinary about the structure of the universe. Galaxies are not scattered randomly. They are arranged in long chains, dense walls, and sprawling webs known as the cosmic web. These structures stretch for hundreds of millions of light-years. Some cosmic filaments span lengths close to 1 billion light-years. 1 billion years of travel for light. 1 billion years of history carried across space. The light year makes this vastness describable, even if still staggering. Now imagine crossing from one side of a supercluster to another. A supercluster is a massive collection of galaxy clusters bound loosely by gravity. The Laniakea supercluster, the structure that includes the Milky Way, spans more than 500 million light-years. When we say this number out loud, it becomes almost surreal. Light leaving one side of Laniakea when early simple life existed on Earth would only now be reaching the other side. 500 million years of cosmic travel. The light year becomes a key that unlocks this unimaginable landscape. But the use of light years does not stop at describing size. It also helps us understand motion. The universe is expanding. Galaxies are moving away from one another because space itself is stretching. This expansion becomes more dramatic at larger distances. The farther away a galaxy is, the faster it appears to be receding. For galaxies billions of light-years away, this recession is so rapid that the light they emit gets stretched into longer wavelengths, a phenomenon known as redshift. Redshift tells astronomers how fast an object is moving away from us and how long its light has been traveling. The light year becomes essential in translating this information. When astronomers say a galaxy is 10 billion light-years away, they mean the light we see from that galaxy has been traveling for 10 billion years. This places the observation in a specific era of cosmic evolution. We are seeing the galaxy when the universe was young, energetic, and chaotic. The light year turns this relationship between movement, time, and distance into something understandable. Consider galaxies at the edge of the observable universe. Their light has been traveling for over 13 billion years. These galaxies appear as faint smudges in powerful telescopes, and yet those smudges carry information from a time close to the universe's birth. Astronomers are not seeing those galaxies as they are today. They are seeing them as they were when the universe was only a few 100 million years old. The light year makes this extraordinary fact both comprehensible and elegant. Even the structure of voids, vast empty regions in the universe, becomes meaningful through light years. These voids can stretch tens or hundreds of millions of light years across. They are like cosmic deserts, regions with almost no galaxies at all. Without the concept of light years, describing these enormous empty zones would be nearly impossible. Light years transform emptiness into measurable form. But perhaps the most astonishing aspect becomes clear when we consider the observable universe itself. The observable universe spans about 93 billion light-years in diameter. This might seem contradictory, because the universe is only 13.8 billion years old. But cosmic expansion means that while light was travelling toward us, the space it crossed was stretching. The light year helps us express this strange reality. We are surrounded by galaxies whose light began travelling when the universe was young, but the distance between us and those galaxies today has stretched far beyond the number of years the light has travelled. This makes the light year not just a measure of distance, but a measure of ancient history. Every galaxy we observe, no matter how distant, becomes a window into a different era. Even stars in our own galaxy reflect ancient times, but galaxies millions or billions of light years away reveal epochs so old they precede the formation of the Milky Way itself. The light year allows us to communicate this journey into the past in a single sentence. This is why astronomers often say that looking into deep space is the same as looking into deep time. The farther we look, the earlier we see the universe. And the light year is the scale that allows us to make sense of this cosmic time travel. This idea reshapes our view of everything. When we see images of ancient galaxies sent back by telescopes, we are not simply admiring distant objects. We are watching the early universe build itself. We are observing the birth of stars, the assembly of spiral arms, the glowing clouds of newborn elements. Light years become the language through which this ancient story is told. The expansion of galaxies over light-year distances also influences our understanding of the universe's ultimate fate. Will expansion continue forever? Will galaxies drift so far apart that their light will no longer reach one another? Light years help us describe these possibilities in clear terms. They help us understand how cosmic distances will evolve over billions and trillions of years. The farther we travel from the Milky Way in thought, the more essential the light year becomes. It allows us to climb from local space to galactic space, from galactic space to intergalactic space, and from intergalactic space to the structure of the universe itself. It connects all scales with a single thread, the steady, constant pace of light moving through time. Beyond the Milky Way, light years become the backbone of cosmic architecture. They reveal patterns that would vanish in the chaos of unfathomable numbers. With them, we can trace the arteries of the universe, understand the great voids, map the superclusters, and visualize the cosmic web stretching across unimaginable distances. And through it all, the light year remains a reminder that the universe, no matter how vast, speaks to us through light that has been traveling toward us since long before humanity existed. Every distant galaxy is a whisper from the deep past, carried across millions or billions of light years. When astronomers began to notice something unexpected about distant galaxies, the entire understanding of the universe shifted. The discovery was quiet at first, buried inside measurements of galaxy light. But as the evidence grew stronger, it became impossible to ignore. Galaxies were speeding away from us, not drifting, not wobbling, not orbiting around some larger structure, moving away. And the farther a galaxy was, the faster it seemed to recede. This observation became one of the most important discoveries in modern cosmology. It confirmed that the universe is not static, it is expanding. This expansion alters how we think about light years. Up to this point, we described the light year as a simple measurement, the distance light travels in 1 year. But in an expanding universe, distances behave differently. Space itself stretches. Galaxies are not just moving through space, the space between them is growing. This means light travels through a medium that is continuously changing. The light year remains an anchor, but the landscape it stretches across is shifting beneath it. The first hint of this expansion came from redshift. When light travels from a distant galaxy, the expansion of the universe stretches its wavelength, shifting it toward the red end of the spectrum. This stretching is like a cosmic fingerprint. The greater the redshift, the faster the galaxy is moving away. And the greater the galaxy's distance, the larger this effect becomes. The relationship is not random. It forms a pattern known as Hubble's law, named after Edwin Hubble, who demonstrated that galaxies follow this expansion pattern at enormous scales. So what does this mean for the light year? It means that when we say a galaxy is 10 billion light years away, we are describing the age of the light reaching us, not the present-day distance of the galaxy. By the time the light arrives, the universe has stretched so much that the galaxy is now far farther than 10 billion light years from us in real space. Its true distance today may be double or triple that number. This distinction between light travel distance and current distance becomes one of the most complex and fascinating parts of cosmology. The light year helps us express the age of the signal, but cosmic expansion adds layers to what that number actually represents. Light years become markers of time, not just location. They show us where the object was when the light left, not where it is today. This dual meaning pushes astronomy into deeper conceptual territory. To visualize this, imagine you release a message in a river that flows gently downstream. At first, the message drifts across calm water, but as it moves farther away, the river widens and deepens, growing faster and larger. The message is still drifting, but the environment is changing around it. By the time it reaches someone many kilometers downstream, the river may look nothing like it did when the message was first released. This is what cosmic expansion does to light. The medium it travels through changes continuously. The expansion also transforms our understanding of the observable universe. The farthest galaxies we can detect emit light that has traveled for more than 13 billion years. But because of expansion, those galaxies are now tens of billions of light years away. The light year still gives us the age of the signal, but the stretching of space means the true distances are vastly greater. Without the light year, this relationship between age and distance would be nearly impossible to express clearly. This also means the universe has a kind of horizon, a limit to what we can see. Beyond a certain point, the expansion is so strong that light emitted today will never reach us. The galaxies beyond this cosmic horizon are not simply far away, they are permanently unreachable. Their light can never cross the ever-expanding gulf. They exist in a region outside our observable universe. This boundary depends on the speed of light and the rate of cosmic expansion, and it is measured in light years. Once again, the light year becomes the essential ruler that tells us what parts of the universe we can study and what parts will remain forever hidden. Even inside the observable universe, expansion affects the shape of cosmic structures. The farther away a galaxy is, the more its light is stretched. At extreme distances, galaxies appear faint, red, and distorted. Without understanding light years and redshift, these faint smudges would be indecipherable. But with them, astronomers decode the deep history of cosmic evolution. They see how galaxies formed, grew, collided, and evolved over billions of years. This time-shifted view of the universe means the light year is not just a measure of cosmic distance. It is a history marker. It tells us how far back in time we are observing. When an astronomer says they are studying a galaxy 9 billion light-years away, they mean they are witnessing the universe as it appeared 9 billion years ago. That galaxy may look nothing like that today. It may have merged with others, collapsed into a larger structure, or faded into a dim remnant. But we are observing its ancient form, preserved in light that has been travelling toward us for billions of years. This creates a strange irony. The most distant galaxies we see are also the youngest. Their light began travelling when the universe was young, so despite being unimaginably far away, we see them at an early stage of development. Meanwhile, closer galaxies appear older because their light has had less time to travel. The light year organizes this cosmic timeline with remarkable clarity. The expanding universe also gives rise to one of the most astonishing concepts in modern astronomy: look-back time. This idea describes how long the light from an object has been traveling. Look-back time is measured directly in light years. If a galaxy has a look-back time of 12 billion years, the light we see today began its journey when the universe was only a fraction of its current age. Look-back time becomes a way of reading the universe like a history book, flipping through chapters that grow older the deeper we observe. This leads to another mind-stretching truth. The observable universe is not the entire universe. It is only the part whose light has had time to reach us. Beyond that lies an enormous region, possibly infinite, that remains invisible. The light year defines the boundary between what we can know and what remains unknown. It becomes the edge of human perception on the largest possible scale. Expansion also affects our interpretations of cosmic motion. When galaxies appear to move faster than the speed of light at great distances, it does not violate physics. They are not moving through space faster than light. Space itself is stretching. The light year helps explain why these galaxies recede from us at rates that seem to defy everything we know. Without the framework of light years and expansion, this phenomenon would be incomprehensible. Through all of this complexity, the light year remains the stable anchor. It gives astronomers a constant reference point in a universe where nearly everything else is changing. Stars evolve, galaxies collide, space stretches, time flows, but the speed of light remains the same. And from that one constant, the light year continues to define the architecture of our cosmic understanding. It also influences how scientists design observational instruments. When planning telescopes, astronomers consider how many light years away the light they want to capture will be coming from. They build instruments capable of detecting photons that have traveled across ancient distances. Without the light year, designing telescopes to view the early universe would have no conceptual foundation. In the end, the expanding universe shows us that distance is not a simple idea. It bends, stretches, and changes with the cosmos. But the light year, rooted in the unchanging speed of light, gives us the ability to describe these changes. It gives structure to chaos. It gives clarity to the unimaginable. It is the ruler that stretches across time itself. Understanding how astronomers measure distances in light years requires stepping into a world of clever techniques, patient observation, and the delicate reading of clues hidden inside light itself. The universe does not come with signposts. No markers float beside stars, telling us how far away they are. Light arrives with no physical label attached. It simply travels through space and lands in our telescopes. Yet from this light, we are somehow able to measure distances across millions or billions of light years. This ability is one of the great achievements of astronomy, built slowly over centuries through ingenuity and persistence. The first method humans developed was parallax. Parallax relies on something simple: a shift in perspective. If you hold your thumb in front of your face and blink one eye at a time, your thumb appears to move against the background. That shift happens because your two eyes look from slightly different positions. Astronomers use Earth's orbit around the Sun to create a similar effect. They observe a star from one side of Earth's orbit, then 6 months later from the other side. This creates a baseline of nearly 300 million kilometers. Against this huge triangle, nearby stars appear to move slightly relative to distant background stars. The movement is tiny, so tiny that early astronomers could not detect it. Stars appeared fixed for centuries because the shift was smaller than the tiniest angle they could measure. Only in the 1830s, with Friedrich Bessel's groundbreaking work, did astronomers finally detect stellar parallax. This moment marked the beginning of measuring cosmic distances with confidence. From the parallax angle, astronomers could calculate the distance to nearby stars. Although this method works only for stars within a few thousand light years, it created the foundation for all later measurements. Parallax is like the first rung on the cosmic distance ladder. Beyond the reach of parallax, astronomers needed new tools. They turned to something stars do naturally. They vary in brightness. Some stars fluctuate in a regular rhythm, becoming brighter and dimmer in repeating cycles. A remarkable discovery came from Henrietta Swan-Leavitt in the early 20th century. She studied Cepheid variable stars in the Magellanic Clouds and found a powerful relationship. The longer a Cepheid cycle, the more luminous it truly is. This meant that by observing the period of a Cepheid's pulsation, astronomers could determine its intrinsic brightness. Once you know how bright something truly is and you know how bright it appears from Earth, you can calculate its distance. This principle is elegant and surprisingly intuitive. If two identical lamps are placed at different distances, the closer one will look brighter. By comparing observed brightness to true brightness, distance becomes solvable. Cepheids became cosmic lighthouses, guiding astronomers into regions far beyond parallax's reach. They enabled Edwin Hubble to measure the distance to the Andromeda Galaxy, proving that it lay far outside the Milky Way, and that the universe was far larger than anyone imagined. Another type of distance marker comes from supernovae, specifically type Ia supernovae. These explosions occur when a white dwarf star in a binary system reaches a critical mass and undergoes runaway fusion. Remarkably, these supernovae all explode with almost the same peak brightness. This uniformity makes them ideal standard candles. When a type Ia supernova appears in a distant galaxy, astronomers measure how bright it seems and compare it to the known true brightness. The difference reveals the galaxy's distance. These supernovae are so bright that they can be seen across billions of light years. They have played a crucial role in modern cosmology, leading to the discovery that the universe's expansion is accelerating. Without them, the idea of dark energy would have remained hidden. The light year ties all these observations together, transforming brightness differences into distance and time. Spectral lines provide yet another tool for measuring distance. Every atom absorbs and emits light at specific wavelengths, creating a unique pattern known as a spectrum. These patterns act like fingerprints. When light travels through space, the wavelengths stretch due to the expansion of the universe. The greater the redshift, the farther the galaxy. This method does not give distance in kilometers directly, but in recession velocity. Combined with models of cosmic expansion, astronomers convert these velocities into light years. In this way, the universe reveals its scale through the light it sends us. Every photon carries information. Its color, intensity, wavelength, and shift tell astronomers how long it has been traveling, what it passed through, and how far its source lies. The light year becomes the natural language for interpreting all these data. As telescopes improved, astronomers built the cosmic distance ladder, an interconnected chain of methods, each calibrated by the one before it. Parallax measures the nearest stars, Cepheids extend to nearby galaxies. Type Ia supernovae reach deep into the universe. Redshift and cosmic expansion models stretch across billions of light years. Each rung depends on the accuracy of the rung below it. The light year provides the final interpretation, translating complex measurements into a clear sense of distance and time. Modern telescopes now refine parallax with unprecedented precision. The Gaia spacecraft, launched by the European Space Agency, measures stellar positions with accuracy so great that it can detect movements as small as the width of a coin on the Moon when viewed from Earth. Gaia is mapping more than 1 billion stars with a precision that would have seemed impossible a generation ago. Through these exact measurements, astronomers calibrate all other methods with increasing confidence. Every improvement expands the map of the universe, stretching the reach of light-year measurements farther and farther. Another tool in distance measurement comes from gravitational waves. When massive objects like black holes or neutron stars collide, they create ripples in space-time. These waves travel at the speed of light and carry information about the event. In some cases, astronomers can use gravitational wave signals to estimate distances independent of light-based measurements. These events, called standard sirens, provide new ways to chart cosmic distances in light years. Radio astronomy also plays an important role. MARSs, natural microwave lasers found in regions of high-energy molecules, can be used to measure distances with remarkable precision. When astronomers observe the rotation of Mars systems around black holes, they can determine distances to galaxies tens of millions of light years away. This adds another rung to the cosmic distance ladder. Through all these methods, one thing becomes clear. The universe communicates through light and energy, and we decode that message using physics, mathematics, and time. The light year becomes the final unit that transforms all this information into something we can understand. It turns brightness into distance, redshift into history, parallax into cosmic geography, and supernova explosions into measurable markers across vast distances. The complexity of these techniques highlights how remarkable it is that we can measure distances at all. We live on a small planet orbiting a single star. Our entire solar system fits comfortably inside a light day. Yet with the tools of modern astronomy, humanity measures distances that reach hundreds of millions, even billions of light years. We read light that began traveling long before Earth had oceans. We measure events that occurred before the solar system existed. We map structures so large that light itself struggles to cross them, and still everything depends on one constant: the speed of light. Without this cosmic speed limit, the light year would not exist. Without the light year, the universe would be a hopeless labyrinth of incomprehensibly large numbers. Instead, with clever observation and careful reasoning, astronomers have transformed the cosmos into something measurable, understandable, and deeply connected to time. The light year represents this triumph. It is the meeting point between physics and imagination, between what the universe reveals and what we can understand. It is the foundation on which we build our maps of the stars, our models of galaxies, and our theories of cosmic evolution. And the more we learn, the more the light year becomes a doorway into new discoveries waiting to be explored. Even after learning how scientists measure light years and how the universe stretches across them, the mind still struggles to imagine just how vast these distances are. Some numbers are so large that the human brain simply gives up trying to visualize them. This is why astronomers often turn to real examples, famous distances that help us anchor our understanding of space. These distances are not just statistics. They are stepping stones that reveal the structure of the cosmos. They show how everything fits together, how far light travels, and how ancient the messages we receive truly are. Start with the closest place beyond Earth, the Moon. It is only 1 light second away. Light takes just over a second to reach it. That means when we see the Moon, we see it as it was 1 second earlier. This is the smallest meaningful example of seeing the past through light. Even here, in our familiar night sky, the delay exists. It reminds us that nothing in the universe communicates instantly. Even the nearest object has a small echo of time. Move outward to the sun. Its light takes about 8 minutes to reach Earth. That means we always see the sun 8 minutes in the past. If the sun suddenly disappeared, hypothetically, Earth would not know immediately. For 8 whole minutes, we would still see sunlight, still feel warmth, still believe the sun was there. Only after those 8 minutes would we understand what happened. This delay is tiny compared to cosmic scales, but it introduces a principle that applies everywhere. Distance is time. Beyond the sun lies the nearest star system, Alpha Centauri, which is a little more than 4 light-years away. This means if a spacecraft travelled at a speed equal to our fastest probes, not even close to the speed of light, it would need tens of thousands of years to get there. Even communication would take years. A signal sent from Alpha Centauri today would reach Earth about 4 years later. This single fact illustrates how enormous even the smallest interstellar spaces are. Next is Sirius, the brightest star in Earth's night sky. Sirius is about 8.5 light-years away. When we look at it, we are seeing a version of Sirius from 8 years ago. Its light began travelling toward us before many modern events happened on Earth, before countless lives changed, before entire cycles of human development passed. Other well-known stars stretch this timeline further. Vega is about 25 light-years away. Arcturus is 36. The famous Betelgeuse in Orion is roughly 600 light-years away. If Betelgeuse exploded today as a supernova, a possibility astronomers often discuss, we would not see the explosion for 6 centuries. Life on Earth, nations, languages and cultures would all continue to evolve, while the light from that distant explosion slowly crossed space toward us. These examples show how light-years turn the night sky into a history book. Each star belongs to a different chapter. Some shine from our recent past, others shine from the time of ancient civilizations. Others shine from eras before recorded human history. As we move farther outward, the scale becomes far more dramatic. Take the Orion Nebula, one of the closest star-forming regions. It is about 1,300 light-years away. When we observe it, we are looking at a scene from more than 1,000 years ago. The stars forming inside those glowing clouds began their development long before modern societies existed. Yet today, we watch their birth through telescopes, receiving light that has travelled across centuries. The centre of the Milky Way lies even farther, about 26,000 light-years from Earth. The light we detect from the galactic centre began travelling when early humans were still spreading across the continents. The great black hole that anchors our galaxy sends out signals that take tens of thousands of years to reach us. Everything we see from the galactic centre is a snapshot from a completely different era of Earth's natural and human history. Now consider distances between galaxies. The Andromeda Galaxy sits 2.5 million light-years away. The light from Andromeda began its journey when early humans first appeared as evolving species. The Milky Way and Andromeda are on a slow collision course, but that meeting will not occur for another 4 billion years. Even in the cosmic timeline, this process is slow and measured. Light years help us understand the immense patience of the universe. Beyond Andromeda lies the Triangulum Galaxy, about 3 million light-years away. Farther still lies the Virgo cluster, a massive collection of galaxies around 55 million light-years from Earth. The light from the galaxies in the Virgo cluster set out before dinosaurs walked the Earth. These galaxies appear to us as they existed during a completely different geological age. The Virgo cluster is only one part of the larger Virgo supercluster, which spans around 110 million light-years. This is a region of the universe containing thousands of galaxies. Light travelling from one side of this structure to the other would need more time than the entire history of complex life on Earth. the scale becomes astonishing. Now leap into the deepest territories of the universe, galaxies billions of light years away. When the Hubble Space Telescope captured the famous Hubble Deep Field image, astronomers discovered galaxies so faint and distant that their light had been traveling for more than 10 billion years. These galaxies were young, small and actively forming stars at the time their light left them. The universe itself was much younger. The deep field revealed a universe filled with countless galaxies, stretching farther than anyone had imagined before. This is where light years become truly powerful. 10 billion light years is not just a measurement, it is a doorway. It tells us that we are witnessing events from a time when the universe was only a few billion years old. It reveals how galaxies looked in their infancy. It shows us how cosmic structures formed, evolved, and grew. Push even farther, and we reach the cosmic microwave background, the oldest light in the universe. This faint glow comes from a time about 13.8 billion years ago, when the universe was young, hot, and dense. This light has been stretched to microwave wavelengths as the universe expanded. When astronomers detect it, they're observing the earliest visible moment in the universe's history. It is not a distant point, but an ancient wall of radiation that surrounds us from every direction. It represents the farthest look-back time we can achieve. These famous distances form the backbone of cosmic understanding. They show how light years structure the universe into layers: seconds, minutes, hours, years, centuries, millennia, millions of years, and billions of years. Each layer reveals a deeper part of the cosmic story. Light years also help clarify the enormous separation between what is reachable and what is forever beyond our physical exploration. Even the nearest star lies several light years away. The nearest galaxy lies millions of light years away. The farthest detectable objects lie billions of light years away. Humanity's spacecraft travel at speeds that turn even one light year into an impossible journey. And yet, light makes these distances feel reachable because it carries information across them. This is the central brilliance of the light year. It connects us to places we can never visit physically. It brings their light, their history, their structure, and their stories into our telescopes. We cannot cross these distances with our bodies, but we cross them with our minds. Famous light-year distances, from the moon's seconds to the sun's minutes to the galaxy's billions, create a scale on which the entire universe can be placed. They remind us of our smallness, but they also remind us that even the smallest species on a tiny planet can measure and understand the universe across unimaginable distances. The light year transforms the cosmos from an unreachable void into a readable book, filled with ancient messages carried across time. As powerful as the light year is, it often gets misunderstood outside the world of astronomy. Many people hear the term and assume it must be a measurement of time. The word year misleads them. It sounds like something that belongs on a calendar, not in a physics discussion. Others imagine the light year describes how far a spacecraft can travel in a year, or how long it takes to move between stars. These misconceptions are common because the universe rarely speaks the same language we use in daily life. Our intuition is shaped by Earth, not by the cosmos. The light year forces us to bend that intuition into a new shape. One of the most widespread misunderstandings is the belief that a light year is a period of time, rather than a distance. The confusion is understandable. Humans learn early that a year is simply 12 months, a complete orbit of Earth around the Sun. But the light year uses the year as a bridge between human experience and cosmic distance. It expresses how far something can travel at the speed of light in that familiar span of time. It is distance disguised inside time. Without this bridge, the numbers would be too big to handle. But because the name sounds like a unit of time, many people misinterpret it as such. They imagine events happening light years ago rather than light years away. Another misconception is the idea that a light year describes how far humans can travel in a year. This is not the case at all. Nothing humans have built comes remotely close to light speed. Even the fastest spacecraft ever created would need thousands of years to travel a single light year. In this sense, the light year is almost the opposite of a practical travel measurement. It shows how unreachable interstellar distances truly are. It acts as a reminder that the universe is vast beyond human engineering, and that light alone can fill those distances with ease. Popular culture also shapes misconceptions. Movies and television often use the light year as a convenient dramatic phrase. Characters speak of travelling light years in seconds, or using engines that jump across light-year distances instantly. Science fiction makes these leaps for storytelling purposes, but they can blur the public's understanding of real science. In reality, no known technology and no known law of physics allows travel across a light year in anything close to instant time. Science fiction compresses the universe for convenience. Astronomy expands it into reality. Another common misunderstanding involves brightness. When people learn that a star is hundreds of light years away, they sometimes imagine it must be brighter the closer we travel to it, like a distant flashlight approaching through darkness. While this is true in principle, the distances involved make such comparisons meaningless. A star might seem bright in the night sky, but travelling closer does not transform it into a sun hovering in front of your eyes. The human mind pictures distance in earthly terms, not cosmic ones. Being 100 light years closer to a star still places you unfathomably far away from it. The light year reveals that close and far lose their ordinary meaning in the universe. There is also the misconception that the stars we see must still exist, shining exactly as they appear. The light year teaches us otherwise. Because we see stars as they were many years ago, some may have changed dramatically, or even died, but we do not yet know. Their newer light is still travelling toward us. Space becomes a place where the present is hidden by distance, and the past arrives disguised as the now. People often imagine stars as eternal, glowing forever in their places, but the light year shows that stars move, change, and evolve, and the sky above us is only a delayed reflection of that ongoing story. Some also misunderstand the scale. They hear that the nearest galaxy is 2.5 million light years away and assume this means 2.5 million kilometers. They do not grasp that 1 light year is nearly 10 trillion kilometers. The scale is so beyond ordinary experience that the mind compresses it into familiar terms. This leads to an underestimation of cosmic distances so extreme that real space becomes almost unrecognizable compared to casual imagination. Even within science fiction, light years are sometimes used as a measure of age. For example, writers might say something is 2 light years old. While poetic, this phrase mixes time and distance incorrectly. A galaxy 10 billion light years away is not 10 billion years old. It might be much older. The light year tells us how long the light has been travelling, not the object's actual age. This subtlety often goes unnoticed, but it changes everything in scientific interpretation. There is also confusion about what we actually mean by distance in an expanding universe. When astronomers say a galaxy is 10 billion light years away, they might mean its light has been travelling for 10 billion years. But because space has stretched, the galaxy itself may now be much farther away, perhaps 25 or 30 billion light years away in present-day distance. The term light year captures the travel time, not the shifting geometry of expanding space. Without this understanding, people sometimes imagine that astronomers contradict themselves, but both statements, travel time and present distance, can be correct at once. The light year also challenges another instinct, the belief that seeing is immediate. In everyday life, when you look at a tree, you see it as it is now, not as it was a fraction of a second ago. But in the universe, sight is always delayed. There is no such thing as seeing the present at cosmic scales. People often forget this fundamental truth, assuming space works like Earth. The light year forces us to reckon with the fact that light needs time to cross vast distances. Nothing in the universe is seen in real time if it is far away. Many imagine that since we see galaxies billions of light years away, we might simply zoom in and see Earth-like planets forming around stars as if we are watching a live broadcast. But what we see is ancient history. The formation we observe happened long before our species existed. There is no zooming into the present. The light year ensures that the farther we look, the older the image. Another misconception is the idea that stars can be measured in kilometers up to any distance. While technically true, the number becomes useless. If you describe the Andromeda galaxy as 2.3655 meters away, the statement does nothing for comprehension. It becomes an empty figure, a mathematical fact stripped of meaning. This leads many to mistakenly believe that astronomers use complicated words like light year just to sound impressive. In truth, the light year exists because ordinary units fail completely at cosmic scales. Without it, astronomy would be a chaotic jungle of monstrous numbers. There's also the popular belief that the light year is the longest measurement we use. It isn't. Astronomers sometimes describe distances in millions, billions, or even trillions of light years when discussing the size of the observable universe or the stretching of space itself. The light year is only the beginning. What gives it special power is clarity, not size. But misconceptions aside, the light year remains one of the most intuitive windows into the universe. It helps people understand their place in a cosmos far older and larger than anything human experience can show. It bridges the gap between imagination and reality. It turns the night sky into a readable text, not a silent mystery. And it reminds us that even though we stand on a small planet, we are capable of measuring distances that stretch beyond galaxies themselves. The light year teaches humility, wonder, and clarity all at the same time. It frees us from the limits of everyday thinking and invites us to understand the universe as it truly is, vast, ancient, and full of messages still traveling across the dark. Thinking about the future of humanity through the lens of light years creates a strange mixture of awe and limitation. On one hand, the light year sets the scale of the universe so clearly that we cannot pretend cosmic travel is easy. The nearest star lies more than 4 light years away. The nearest galaxy lies millions of light years away. And the farthest regions of the universe are separated from us by billions of light years. These distances dwarf everything humans have ever attempted. Even the greatest voyages in human history, crossing oceans, continents, or even the moon landing, are microscopic compared to the scale of a single light year. Yet the light year also reveals the potential for human imagination. It shows that while our technology is small, today our curiosity is not. The desire to explore beyond Earth has been part of human nature since our ancestors first looked up at the stars. The light year becomes a symbol not only of distance, but of ambition. It sets a challenge and invites us to dream of bridging the unimaginably vast. To understand the scale of this challenge, consider the fastest human-made object to date. It travels at speeds of tens of thousands of kilometers per hour. Impressive by earthly standards, but painfully slow in cosmic terms. At that speed, it would take tens of thousands of years to travel a single light year. Human civilization would have to survive longer than recorded history for such a journey to succeed. Even communication becomes asynchronous at cosmic distances. A message sent to a probe 1 light year away would take a year to arrive and another year to return. Our current tools barely scratch the edge of the cosmic map, but this limitation does not stop visionaries from imagining what future travel might look like. Some scientists propose generational starships, vast vessels where entire families live and die while traveling across light years. Others imagine cryogenic sleep, where humans or their descendants sleep through the voyage. Some propose robotic probes that travel at a fraction of light speed, sending back data over decades or centuries. Even more ambitious ideas include fusion engines, antimatter propulsion, light sails pushed by powerful lasers, or hypothetical technologies that manipulate space-time itself. One such proposal is the concept of a light sail. This idea uses an enormous, thin reflective surface that captures momentum from photons. Light becomes the engine. When hit by high-energy lasers, the sail accelerates without fuel. Projects like Breakthrough Starshot hope to send tiny probes to the Alpha Centauri system within decades rather than millennia. The probes would still not travel anywhere near light speed, but they could reach a significant fraction of it. A 20% light speed journey would still take more than 20 years to reach the nearest star, but this is a giant leap from thousands of years. Fusion propulsion is another possibility. Stars themselves generate energy through fusion, and humanity has spent decades trying to harness this power. If we could build a fusion drive capable of sustained operation, spacecraft could push themselves through space at far greater speeds than chemical rockets. This would cut multi-millennia journeys down to centuries or decades, still far from instant, but much closer to the realm of possibility. Antimatter propulsion sits even further in the future. Antimatter annihilates ordinary matter with incredible energy. If controlled safely, it could drive a spacecraft with unmatched efficiency. But generating and storing antimatter remains extremely difficult and dangerous. Even so, these ideas show how the light year inspires innovation. The vastness encourages us to reach higher, think bolder, and imagine future technologies that push beyond our current limits. Some scientists go even further and explore theoretical physics for answers. Ideas like the warp drive, wormholes, or bending space-time emerge from equations that allow shortcuts through the fabric of the universe. These ideas do not violate physics on paper, but they require energy levels and exotic materials beyond anything humanity can currently produce. Still, they remain a part of the scientific imagination because they represent hope. Hope that one day, perhaps far in the future, humans might find a way to travel not through space, but around it. Even without interstellar travel, the light year shapes the future of astronomy. As telescopes grow more powerful, we will peer deeper into the past. We will observe galaxies farther and earlier in time. We will study the birth of stars, the formation of black holes, and the evolution of cosmic structures across billions of years. Light years tell us the scale of what we can observe and how far we can look. The James Webb Space Telescope has already shown us galaxies from a time when the universe was only a few 100 million years old. Future telescopes will push this boundary even closer to the Big Bang. Each improvement allows us to read earlier chapters of cosmic history. Light years define the timeline of these discoveries. They tell us how ancient the light is, how far it traveled, how the universe has changed over time. Light years also influence the search for life. When astronomers discover planets around distant stars, exoplanets, they describe their distance in light years. This immediately tells us two things: how challenging it would be to travel there, and how ancient the light is that reveals the planet's existence. If a planet is 100 light years away, then the information we have about it is already 100 years old. Any changes that happened in the last century are unknown to us. This creates a strange relationship between discovery and delay. Every planet we find is an echo of its past state. Still, the search continues. We now know thousands of exoplanets exist. Some lie in habitable zones where liquid water might be possible. Some are rocky worlds, similar to Earth. Some may have atmospheres, but they all lie across light years of space. Their signals, tiny dips in starlight or faint spectral lines, must travel across those light years to reach our instruments. The light year becomes a reminder that even if life exists elsewhere, communication will be slow, limited by the speed of light. Consider a hypothetical intelligent civilization 50 light years away. If they detected Earth today, they would be seeing our planet as it was 50 years earlier. Any signal we sent would take 50 years to reach them, and their reply would take another 50 years. A full conversation would span a century. This reality shapes how scientists think about communication with extraterrestrial intelligence. Light years define not only distances, but the structure of possible relationships between civilizations. Even on the scale of human futures, light years play a role. As Earth faces challenges, climate change, resource depletion, natural limits, some thinkers imagine that humanity might one day need new worlds. But the light year reminds us that escape across the stars is not simple. The nearest habitable worlds we have detected lie dozens or hundreds of light years away. Even if they existed in perfect condition, reaching them with current technology is impossible. The light year forces us to think realistically about the future. Our first responsibility is to care for Earth. Yet the light year also shows us that the universe is full of possibilities. Billions of galaxies, billions of planets, countless environments where life might thrive. We may never reach them physically, but we can observe them, learn from them, understand them, and dream about them. The light year bridges the gap between our physical limits and our infinite imagination. It teaches us that the universe is vast but not unreachable in knowledge. It teaches us that time and distance are intertwined. It teaches us that light carries the stories of ancient worlds to us across unimaginable expanses. And it teaches us that curiosity is a force as powerful as gravity, pulling us toward the unknown. In the silence between stars, the light year becomes our guide, a measure not only of distance, but of hope. As we reach the end of this journey through light years, the story settles into something larger than measurement, larger than astronomy, even larger than science itself. It becomes a story about perspective. The light year began as a practical tool, a solution to the problem of describing distances too large for ordinary numbers. But as humanity grew more skilled in observing the universe, the light year transformed into a window into existence. Through it, we see not just where things are, but when they were. Through it, we learn not just how far the universe stretches, but how deeply it remembers. Every time you look at the night sky, you're witnessing an arrangement of stars that does not exist in the present tense. Each one is a lantern from another moment in cosmic history. You are surrounded by ancient messages that crossed oceans of darkness to reach you. Some traveled for years, others for centuries, others for thousands, or even millions of years. The light year gives meaning to these journeys. It gives each star a place in time. And this reveals something profound. To see the universe is to look into the past. There is no other kind of seeing at cosmic scale. The light we observe is old. The events we capture in telescopes have already happened. The universe becomes a vast archive, and we are readers of its ancient records. Every photon is a piece of information that traveled unbroken across unimaginable distances. It arrives carrying stories of birth, death, collision, explosion, growth, and decay. Stories written in the language of light. This understanding shifts our place in the cosmos. For most of history, humans saw themselves as central and significant. The sun rose and set for us. The stars decorated our skies. Myths placed humanity at the heart of creation. But as we measured distances in light years, our understanding expanded. We realized Earth is not the center of anything. Not the solar system, not the galaxy, not the universe. We are a small presence on a small planet, around a small star, in a minor arm of an ordinary galaxy, among trillions of galaxies. This realization could feel humbling to the point of insignificance, and yet it does the opposite. It enlarges what it means to be human. Because from this small world, using nothing more than our curiosity, our intelligence, and our instruments, we have measured distances across billions of light years. We have mapped a universe so large that a beam of light, the fastest thing that exists, would need billions of years to cross it. We have understood cosmic structures that our ancestors could not have imagined. The light year becomes a symbol of our ability to reach beyond our limits. When we describe something as 5 light years away, or 50 million light years away, we are demonstrating not weakness, but incredible strength. We are proving that the human mind can stretch far beyond the boundaries of the human body. We may never physically travel these distances, but mentally, mathematically, and imaginatively, we cross them every day. And while the light year reveals our smallness, it also reveals our connection to the universe. Light travels freely. It moves across the emptiness without hesitation, carrying information from distant suns to our retinas. In that sense, the universe communicates with us constantly. It shares its history with anyone willing to study it. We do not need to be powerful or large to understand it. We simply need to observe and learn. The light year makes that possible. It also reminds us that everything is temporary. Stars burn out, galaxies collide, planets form and vanish, and even the universe itself changes over time. But light preserves these moments. It holds them, carries them, and delivers them across time. When we observe a distant galaxy, we are seeing a preserved moment of cosmic youth. When we observe a star cluster, we are seeing a fossil from billions of years ago. The universe changes, but its memories travel endlessly. The light year is the measure of those memories. This idea leads to one of the most beautiful truths in astronomy. We are all made of ancient atoms forged in stars billions of light years away. The elements that form our bodies were created in stellar furnaces and scattered across space by supernova explosions. Those materials traveled across light years before collecting into planets, oceans, forests, and living beings. In a very real sense, we are descendants of ancient light and ancient stars. The light year is not just a measure of distance, it is part of our origin story. The future of astronomy will push this understanding even further. New telescopes will look deeper into space and further back in time. We will observe galaxies closer to the dawn of the universe. We will study exoplanets with incredible detail. We may even detect signs of life across light years of separation. And every time we make a discovery, the light year will remain the measure that guides us. It will tell us how long the light has traveled, how old the information is, and where it sits in the cosmic timeline. Even as technology advances, even as our understanding deepens, the light year will remain a constant reminder of the universe's scale. It is elegant, simple, and profound. It expresses a truth that no other unit can capture, that distance and time are inseparably woven together in the fabric of the cosmos. And as humanity continues dreaming of interstellar exploration, the light year stands both as a barrier and an inspiration. It shows how far we must go, but also how far our minds have already traveled. It reminds us that progress is slow, but imagination is fast. That we may not touch distant stars with our hands, but we touch them with our understanding. In the end, the light year tells a story about our species. It tells a story of curiosity strong enough to reach across billions of years. It tells a story of a tiny planet that dared to measure the universe. It tells a story of light, steady, patient, ancient, moving through darkness to reveal the truth of existence. When you look up at the night sky, remember that you're not just seeing stars, you're witnessing time itself flowing towards you in thin, quiet streams. You're standing inside a universe that has spent billions of years sending light your way. Every star, every nebula, every galaxy is a messenger, and every message has crossed light years to reach the eyes of someone curious enough to look up. This is the legacy of the light year, a unit that measures not just distance, but our ongoing conversation with the cosmos. It is the bridge between what is out there and what we can understand here. It is a symbol of the universe's vastness and humanity's endless desire to explore it. And as long as we keep asking questions, as long as we keep observing, imagining and learning, the light year will continue guiding us across the greatest distances that exist. Distances not only of space, but of understanding. As we reach the end of this journey, the idea of a light year feels less like a number and more like a window into the universe. It shows us how far light travels, how deep time stretches, and how much of the cosmos we can understand from right here on Earth. The night sky is no longer a silent picture. It's a record of ancient moments still traveling toward us across unimaginable distances. If this video helped you see the universe a little differently, don't forget to like the video, subscribe to the channel, and share it with someone who loves space as much as you do. There are countless mysteries waiting out there, and we'll explore them together, one story at a time. Thanks for watching, and I'll see you in the next journey through the cosmos.